Hello, my name is Francis Poulin, and I'm very happy to be presenting this on behalf of myself, my co-authors, Henry Gould, Greg Wagner, Ali Ramadhan, Valentine Churavy, and Chris Hill. And the title of the talk is Scaling of Oceananigans.jl on multi-GPU and CPU systems. And below, or on this figure, you'll find a picture of something that was created with Oceananigans that models the evolution of the ocean, showing some of the interesting features that you find at the surface of the ocean. So Oceananigans has a paper that introduced it in 2018 in the Journal of Open Source Software, the authors of which are listed there. And Oceananigans is a library that simulates the evolution of the ocean. In simplified context, it is a finite volume model. It includes rotation. It allows for fluids to be stratified and describes fluids that are commonly called in the area of geophysical fluid dynamics. It is written entirely from scratch and is strongly based on the MIT general circulation model that has been around for almost 20 years. There are a lot of options that are available in terms of the physics and the numerics, some of which I'll talk about very soon. And one key feature is that it does aim to be fast and friendly and does run on two different architectures, namely GPUs and CPUs. There are two ways of parallelizing the simulations. One is through MPI.jl and the other is multi-threading. So some of the bells and whistles that you'll find that are contained with Oceananigans is that it does allow for either rectilinear or curvilinear grids. The number of spatial domains can be 0 to 3. As I mentioned before, it uses a finite volume discretization and high ordered vection schemes in order to try to obtain the best very high accuracy that you can given a particular resolution. It does describe fairly general fluids, but it can also be used to, in particular, describe ocean physics really well, which is one of the key features. And for those of you that know something about ocean physics, there are three different models, one of which is what's called the Boussinesq non-hydrostatic model. The other is a Boussinesq hydrostatic model. And the third is a shallow water model. And some of the forces or features that are included are the Coriolis force, a nonlinear equation of state for seawater in order to try to describe that more accurately. You can have as many passive tracers as you like, and there's a variety of closure schemes for large eddy simulation. And in this figure, you'll see a plot of the convergence rates that you obtained contained in Oceananigans to validate what's predicted from theory. And you will see the agreement is very close, and the order of accuracies for these ones go as high as fifth order. Now, when simulating ocean flows, we want to use as much computing power as we can in order to resolve different features about the ocean. That's why parallelization is very key, and there are two essential ingredients that need to be done. In simply evolving a field, say the density forward in time, it's prognostic and it uses local behavior in terms of what is true or what is known around that point. But when you're determining things like the pressure, which is crucial in these sorts of calculations, it's diagnostic and it's global because you need to know the value of the fields everywhere. And that is something which makes things very complicated. It's not contained in the shallow water model, but it is necessarily contained in the other two models. Now, in terms of the parallelization using MPI, we've computed both weak and strong scaling for both shallow water model and incompressible model. I'm showing you the results here for shallow water model. The efficiency is on the order of 80% for 128 cores. And it goes to show that we are doing very well. As I mentioned, multi-threading is not doing so well, which is why I'm not showing you the results yet. Hopefully next year, if not sooner. And one of the big key features, as I mentioned before, is be able to do things on GPUs, since GPUs can do things faster. And we find that in the case of the incompressible model, when we have a grid of 256 cubed, typical advection schemes give you speedups of around 200 times, whereas Uno 5, one of the better ones, gives you a speed up of 400, in part because this is a really expensive scheme and GPUs seem to perform favorably on this approach. That means that if you have one CPU core doing a calculation over 24 hours, the GPU can do it less than 4 minutes. And here you see both for float 32 and float 64. Now, an interesting idea that we're playing with is we know that GPUs can be faster. We also know GPUs can be a lot more expensive. In particular, 32-thread Intel node can be around $6,000, whereas a 32-gigabyte NVIDIA V100 is around $15,000. So we're trying to define the idea of cost effectiveness and thinking about the points per second per dollar. The higher, of course, means more bang for your buck. And for different calculations we've looked at, we find that for the CPU case, it's on the order of over 12,000 points per second per dollar, whereas the CPU, it's more like 26,000 points per second per dollar. And the ratio of these two is 2.14, which means that by this metric, the GPU is more than twice as much cost effective. Now, I'm sure there are other interesting ways to quantify this, and if you have ideas, please let us know. But just to conclude, I mentioned some of the interesting features of Oceananigans. I want to emphasize this is something that is useful for research and teaching as well. In terms of studying oceanographic problems or problems in the regime of geophysical fluid dynamics, using different architectures, CPUs or GPUs, can make things, you can do some comparisons if you're interested and sometimes speed things up. We can parallelize things as well as include some other interesting physics that we mentioned before. We want to make everything efficient, accurate, and also easy to use. We are developing different geometries, and feedback we would like from the community is in order to figure out how do we make things easier. So hopefully people can try it and let us know. How can we improve the efficiency and the scalability? And where might these tools be used elsewhere? So please check us out on GitHub, and thank you very much for your time. And these are some of our sponsors. Thank you very much.